Well, welcome back to our session. We'll talk a little bit about load balancing. As we're going back, as I started talking there, we really came up with this concept for guidance about 2 years back, as we told our customers, well, now that we've moved all client access in front of the CAS server, one of the things you'll need to do is put a load balancer for all client access. So in the past, you needed to load balance the HTTPS services, such as Exchange Web Services or Outlook Web App, for example. But now we've actually moved Outlook as well, right? So Outlook MAPI access is also behind the CAS servers. And so our guidance had put a load balancer out there, load balancer services, and customers started to do that. We realized we need a little bit of guidance. There's a lot of different client connection methods to get to Exchange. We could come in from a Outlook client using MAPI, Outlook client using Outlook Anywhere, an ActiveSync device, Outlook Web App, Exchange Web Services, POP or IMAP, etc. And we started releasing more and more guidance. And our little 3-page white paper turned into 10 pages, turned into about 20 pages. And we realized that we were getting into actual load balancer specific settings. And at that point, instead of providing or having us write the guidance for all the different load balancers on the market, we started to engage with the load balancer teams. And so a group of us sat down with all of them, we put together a program. Now you'll see all the major load balancing vendors actually releasing guidance specific for Exchange 2010. In this session, what we're going to do is give you a background of the principles in Exchange that the load balancer vendors are going to follow. We'll also give you a little bit of overview of the principles of load balancing, the different routing options, for example. We've got multiple ways to route packets from a client to the CAS server and back. We have some options and discussions around persistence, as well as concepts such as SSL offload. So all of these are different themes or topic areas you'll have to explore as you develop your load balancing infrastructure that sits in front of Exchange. Towards the end of that, we'll give you a demo. We also list all the hardware vendors that have load balancers compatible with or provide guidance for Exchange 2010 today, and a little feature matrix or table around that. If we look back in time, if you go all the way back right into the 70s and 80s, customers or hardware vendors and software vendors use the scale-up approach. You would add more processors to your mainframe or your mini computer. You would add memory to that. And so you always had a single endpoint for your clients to reach. You added scalability inside of that endpoint versus actually scaling out. But by the late 90s, you saw a separation from that towards the client-server model and eventually towards the web-based model, where you had application servers that would be spread out into an N-tier model, and you had some sort of load balancing algorithm or infrastructure in front of those. It could have been application specific, or you could have required some sort of device or functionality that actually selected one of those application servers for you. We developed a capability or technology called Windows Network Load Balancing, or WNLB, back in the NT4 days. We've carried that technology through in Windows for today. You run WNLB, for example, on 2008 R2. But what we find, especially as we start to go into medium or high scale environments with WNLB, is that there's a significant list of technical issues that really constrain us from providing the optimal load balancing experience as we get to applications such as Exchange 2010. The simple one, right, the first one is if we use the WNLB in unicast mode, you're going to be subject to the concept of switch or port flooding. Your network infrastructure team typically will complain about that and want you to turn that off or change the method that you're going to be providing load balancing. Another knock against WNLB is the concept of NAT and the persistence options. We can only do source IP for a persistence or an affinity option with WNLB. We don't have options such as SSL session ID or cookie-based persistence that we'll talk about later. We do hit scalability issues as we call out over 8 nodes. There's no service or health awareness checking, so we can't actually validate that the Exchange CAS server is listening on /OA or the Exchange services are running and are healthy on that back-end infrastructure. Of course, if we look at the simplest Exchange 2010 configuration in a 2-server multi-role config, and we want to extend the database availability concept with a DAG or replicate the data between those 2 servers, we install Windows failover clustering underneath for you automatically. And so you essentially are configuring an Exchange or a Windows cluster when you set up an Exchange DAG. And it turns out, as we're going through and looking at this 2-server model a couple years back, right, that we require Windows failover clustering for the heartbeat mechanism in the database availability group. but also we need to have some service awareness or service load balancing capability for CAS. And so we went back to the Windows group and said, hey, can you support for us the concept of running WNLB and Windows failover clustering on the same two physical boxes or same two virtual instances? And they kind of came back to us and said, you know, are you crazy? Who runs, you know, most customers would pick, or most applications will pick one over the other. It's not typical for an organization to want to run WNLB and Windows failover clustering. And so we didn't get a support statement back on there, and we can't run, therefore, WNLB in that two-server model. So either you'll have to break out the server roles and add some cost around complexity and operations to your Exchange infrastructure, or put some sort of network load balancing device in front of those two multi-role boxes to provide that simple two-server model for Exchange 2010. What we also found is that over the past 10 years especially, the load balancing vendors went from providing basic, what we call layer 4 load balancing, or doing some sort of source IP persistence, into providing a much richer feature set. And so if you're looking or evaluating your load balancing vendors, you might see that they're not even called load balancers anymore. They prefer the nomenclature application delivery controllers. They'll be doing things such as checking for the number of connections to a specific server for their load balancing algorithm, right? They may have application credential logon or authorization policies that they can enforce in the perimeter network, offloading some of that from your existing reverse proxy infrastructure, providing essentially a reverse proxy capacity or capability. There's features such as smart compression for in a high-scale environment. They're actually not compressing certain data to clients if that client's on a high-speed connected network. So if we have low latency in the less than 50 or 100 milliseconds, for example, and the client has a several meg connection for a high-speed internet access at home, or they're coming in over a LAN, it's actually faster for that connection to not press the data flowing over it. That compression takes some processor time on the load balancer to compress and some processor time on the client to decompress. And so on the fly, they'll be actually dynamically adjusting things like compression to ensure that optimal client experience. Going back, before we had a lot of processor capability, there was the concept of SSL offload or bridging, where we could have the device itself or an ASIC chipset providing SSL termination and then have an HTTP connection back into our CAS server infrastructure. That would offload the SSL requirements on CAS. We see less of an issue with that today as we start to see the core counts in servers go up significantly, and we have a lot of those CPU cycles available. But once in a while it does come up if we start to see the higher bit length certificate. So if we're pushing a 2048 or a higher bit length certificate, we still can see some processor impact in a high scale or large scale organization around that SSL processing to decrypt the communications. So in some cases it may make sense to do SSL offload. We'll actually go through and talk a little more about that later in the session. Like we said, there's also the concept of rate shaping or TCP packet stream modifications, where it's dynamically adjusting the window size during the session to ensure that optimal speed. So as a result, we're seeing more than just the basic layer 4 load balancing capabilities. We're seeing a much richer set of processing essentially happening in that perimeter network or in that boundary access zone where clients come in to connect to Exchange. The next part of this presentation, we're really going to focus on kind of three areas. The first one is the concept of how do we route packets from our clients to the CAS server infrastructure. And we have a few choices on that. The three supported choices from Microsoft for Exchange 2010 is the concept of SNAT, what we call the load balancer as a default gateway, where we set the default gateway on the CAS servers to point to the load balancing or the load balancer device, as well as an option called direct server return. And we've got some nice animations that will walk you through these different routing options. We found that this has been a high point of confusion both inside Microsoft and outside as customers try to grapple with how do we actually configure our CAS infrastructure and our clients with a load balancing topology. There's also the terminology aspect. We've made the comment in the past that in the Exchange 2000 and 2003 timeline, we found a lot of our Exchange admins were becoming storage experts because you had to carve out and modify the storage in a certain way to ensure an optimal client experience. If you didn't want the little RPC dialog pop-up box, you had to ensure that not only did you have enough capacity inside of your storage infrastructure, but you also needed the the I/O capability to meet the I/O characteristics of Exchange, which were significant at the time. We spent a lot of work, you probably saw over the last couple of decades, decreasing the I/O requirements in Exchange in 2007 and 2010. We put a few of our best developers on that for the last 6 or 7 years, and we've decreased from 2003 now 92% of our I/O capacity, right? So that storage aspect planning has become, it's still an important part of your role, but it's not as critical as it was 10 years ago, as now we're enabling a lot of the lower cost, cheaper storage options that have high capacity, but that lower I/O threshold. But in 2007, we took some steps around security. So we wanted to not just secure clients talking to the CAS server infrastructure, we wanted to encrypt by default all traffic on the wire. And so we deployed certificates for hub transport and for CAS to help guarantee or ensure the integrity of communications. And as a result, we saw you kind of came as a certificate expert. It was probably the first time for a lot of you that you worked with the concept of a subject alternate name certificate and some of the complexities around multiple namespaces with Exchange. And so you became familiar, in essence, with the terminology and vernacular of a certificate or a CA infrastructure. And what we're saying now is with Exchange 2010, you're kind of taking that knowledge again, and our goal is to help you become familiar with the load balancing side. Either you will be configuring these load balancers directly, or you'll be engaging with someone at your organization, right, that runs the load balancing infrastructure, and you have to use the same terms and language to ensure that when they're doing the configuration, we don't have problems with timeouts or drop connections for clients talking to the Exchange side. So we'll talk a little bit about the terminology associated with load balancing. At the simple level, there's really kind of two ways to deploy a load balancer in your environment. And we sum those up as what we call a one-armed config and a two-armed config. And in essence, it's very simple. Either the load balancer has one connection to a network subnet, and it has both the load balancer management IP addresses as well as the virtual IP addresses on that single interface connected to a single subnet, or the load balancer straddles two or more network subnets and therefore has a leg or a network interface on two different subnets. So one subnet possibly your server infrastructure and a management interface, another subnet internet facing or client facing that's on a different network subnet. And so when we talk about the concept of two-armed, we now have some discussions of how do we route traffic for clients trying to talk to Exchange and those Exchange servers coming back to the other side. And so we've got some options in that routing that we talked about earlier, the concept of source NAT or SNAT, as well as the concept of load balancer default gateway versus the concept of direct server return. So SNAT, and as we'll talk about later, turns out to be the recommended one in most scenarios, is the simplest version of this, right? So here we take a single-armed load balancer. We can see that it has a management or a self-IP right on the 10.5 network. It also has a virtual IP or a VIP on the 10.5 network as well. In essence, we only have one interface attaching to that network subnet. We've got clients also on the 10.5 network. So client sends a packet to the virtual IP address. This could be an OO request or an Outlook request, for example. That IP address has a source IP of the client, 5.201, and a destination IP of the virtual IP address that resolved it in DNS from mail.contoso.com and got 10.5.5.31. With SourceNAT, when that packet hits the load balancer will go through an algorithm to select one of the CAS servers in our array. It could be round robin, it could be least connections, it could be weighted connections, for example. We'll talk about how it selects one later, but it makes a decision to select one. In this case, it selects CAS server 2. The difference here, though, with SNAT is the load balancer now changes the source address of that IP packet. So we see that when that packet arrives at the destination CAS server, the destination IP address is 5.82, but the load balancer changed the source IP from the client's 5.31 to the load balancer's 5.11 address. And so what SourceNAT is doing is by changing that source IP is telling the CAS server, when you reply to this packet at IP layer 4, send it back to the load balancer. If it didn't change that source IP address, the load balancer would send the request directly back to the client, 5.201 in this case. The client sent out a request to 5.31. If the IP stack receives a reply from 5.82, it looks like a problem, right? The client's not expecting a reply from 5.82. So somehow we have to ensure that when the client routes back from, or the packet routes back from the CAS server to the client, it has to go back to the load balancer, or it has to have that .31 address, right? So in this case, SNAT will do that for us. Packet comes back to the load balancer, changes the source IP of the packet to 5.31, so when the client receives a reply to the request, it appears to came from the source that it actually sent the original packet to, and the TCP session will accept the packet. We don't have a problem with MAPI. Connection is established, and we have an Outlook session or an OWA session or an ActiveSync session, for example, successfully in this case, going from the client off to the CAS server. So you guys clear on the concept of SourceNAT? Change the source IP address. We have proper routing back to the client when that packet originates. Let's talk more then about, so SNAT of course could work if the load balancer is one-armed or two-armed. We just show you the sample in this case of a one-armed config. Let's look again at another option that we call direct server return. So in this case, we've also changed the topology. We now have a two-armed topology, right? So, sorry, this is still single-armed, my bad. Next one we'll show you the two-armed. Now we're going to do direct server return from the load balancer back to the client. Original packet comes in, heads to 5.31. Source IP, as we see, is the 5.201. Load balancer sends the request off to the CAS servers, but it does not change the source IP using SNAT. It just forwards that packet to a CAS server and leaves the source IP as the 5.201. So in this case, the CAS server is going to reply directly back to the client. When it replies back to the client, when we configure direct server return, we have to do some additional configuration on our CAS servers. The CAS server has to have a loopback address added to the network interface, and it has to have the 10.5.5.31 VIP address associated on that loopback address, which we'll show you later. Therefore, when the reply returns, it looks like it's coming from 5.31, client accepts the packet, and we're off and running. Main difference here, right, is the traffic is not flowing back through the load balancer. The con in this scenario is we now have to manually modify and keep up to date our CAS server network configuration every time we add or remove a CAS server to that pool or perform any maintenance on those CAS servers. This requires some overhead administration. It's easy to forget to do that on one of your servers. As a result, you'll see random problems when clients connect to the server that's not changing the source IP address to the VIP address going from CAS back to the client. The benefit in this case with direct server return is that because the traffic does not flow back through the load balancer, we reduce the traffic flowing through the load balancer. This is a common routing scenario if we're looking at streaming video or large content types flowing back to the clients, right? So in this case, we don't have to provision a higher end load balancing infrastructure. The servers will return that traffic directly to the client. We can have just a layer 4 routing decision occurring at the load balancer, and that traffic will flow directly from the servers to the clients, and we have reduced network throughput and reduced number of connections essentially on our load balancing infrastructure. It's possible to configure this with Exchange. Let me give you the steps a couple slides later. Like we said, due to the increased overhead administration, this is the least common of the typical routing options that we see deployed for 2010. And there's one more, right? In this case, we're going to do a dual-arm configuration using SourceNAT. So in this case, we've got a load balancer attached to two separate networks. One of them is client-facing. That could be a public, untrusted network, for example. That could be an internal network that has clients on it. In this case, it's the 10.5.5 network. Our server infrastructure, however, is located on the 172.16 network. So we have two different network interfaces. Client sends that first packet to the load balancer VIP, 10.5.5.31. We have SNAT turned on, so the load balancer changes the source IP of that second packet to the 172.16 address. Packet hits the CAS server. Packet replies to that 172.16, which is the load balancer management interface. Load balancer again nats that packet, changes the source IP to 5.31. Request goes back to the client. Client receives the request from the IP address it sent the original request to, or receives the reply, and therefore accepts that trusted communication. So we can see that SNAT will work in either a single arm config or a dual arm configuration. In both the single arm and the dual arm configuration, if we need that, or especially in the dual arm config, right, if we need that traffic to route back and we don't enable SNAT, we need to have the CAS servers configured with the load balancer as the default gateway. So another way to force this traffic to route back to the client is configure the CAS servers to route traffic for the 10.5.5 network through the 5.21 IP address. So in that case, they'll receive a request from the client on 5.201. They have a route that says route traffic for 5.201 through 5.21. In that case, they send it to the load balancer. Load balancer does some basic IP4 routing and sends the packet off to the client on the from the 5.31 interface, which the client is expecting. So like we said, there's some additional steps required when we talk about the concept of direct server return. First of all, we have this concept of MAC address translation, where we're actually not doing network address translation, but we're going to translate the MAC address in that direct reply. We do need the virtual service on the load balancer right to route the clients directly to the CAS servers. We don't want to change those IP addresses because the load balancer needs to see that client IP address to return. We put the loopback adapter on, and as well, we don't have the options around some of the higher level persistence types. One benefit to direct server return is the aspect that the client logs, or the server-side logs on your servers, will actually have the client IP addresses. So if you're looking at doing troubleshooting from a CAS perspective, right, having the client IPs in those server logs provides you the capability to see which client was submitting a particular request, because the load balancer is not routing or translating with SNAT those source IPs as it flows through the load balancing infrastructure. When we use SNAT in a very large-scale environment, we have some limitations around TCP communications. And so in each source IP to destination IP communication stack, we have a limit of 65,535 connections. So from each load balancer management interface to a specific CAS server inside of the pool, we get 65,535 concurrent connections. This typically isn't a problem because it's easy for us to add an additional CAS server to the pool. It's relatively rare we see that 65,000 connections exhausted against a particular CAS server in the array. But in some cases, it's required then to, or the workaround for this is to use multiple IP addresses on the load balancer, or a pool of addresses, to provide SNAT capabilities. So if I look back on the previous slide, right, instead of just the management interface, I may define a pool of 3 to 5 IPs. I now have 65,535 connections per IP address in that pool for each of the recipient CAS servers. So if I put 3 addresses in the pool, I get the equivalent of 180,000 concurrent connections to each CAS server inside of the array. The issue with an SNAT pool when it comes to MAPI is that MAPI requires all communication from that client to the CAS server in that pool to come from the same SNAT address. So if we do have this configuration where we require a significant higher number of IP addresses, we do have to ensure that the load balancer keeps track of client A and always uses IP address number 2 when SNATing requests from client A. So there has to be a one-to-one correlation from the client to the IP address in the SNAT pool. That feature, excuse me, that's one of the features that causes your load balancer cost, for example, to jump substantially. It's typically easier and or cost effective to add another CAS server to the array for a couple of $1,000s versus the possibly $50,000 to upgrade to one of these feature levels. So a simple solution for using SNAT. If you talk to your load balancing team, right, use a single IP address. I don't have to worry about correlating the client requests to an IP address in your SNAT pool, because you only have one IP address used for SNAT going forward. As we said, right, direct server return is the option that would give you the client source IP on your server-side logs. If you're using SNAT, we're going to hide that IP address from the server logs. We've actually introduced an X header in Exchange 2010 and from our clients that will allow you to leverage the X header capability versus the client IP. So if you are using SNAT, you have the ability to track in the logs the header information there instead of actually going with just the IP address in your server-side logs. Another high-level point to look at, right, is the concept of node, host, and member and server. The particular one here is a member. A member of a load balancing array is not just a server in that array, but is an IP address plus a TCP or UDP port combination specifically. So if you're talking to somebody in your load balancing team, when you find a member, you're defining an IP address plus a port combination for that back-end infrastructure. So that's a lot of information on these routing options. Again, there's 3, right? SNAT, which we've given you kind of the scenarios for there. direct server return, which has some pros and cons, and load balancer default gateway, again, some pros and cons. So if you're looking for the quick summary, we put a slide up there, and we also called out what we recommend typically for customers to deploy in their Exchange 2010 infrastructure. Any questions on the routing options you'll have with load balancing? Does that help kind of provide some background as to the different conversations you'll have or planning you'll have around the routing capabilities? See a few heads nodding. The next topic that we'll jump into is the concept of persistence, or affinity, or stickiness, as it might be called. What this refers to is that when I have a request coming in from client A, I want all future requests from client A to go to the same CAS server in the pool. So if client A's first request is directed to CAS server 3, all subsequent requests from client A should also go to CAS server 3. And so there's some different ways we can provide that stickiness or the persistence. The most common is something called source IP. We just have a table that lists the source IP of our client. We know that source IP 5.201 always goes to CAS server 2. We just ensure that all subsequent requests from 5.201 go to CAS server number 2. But there are some technical issues around NAT that we'll show you later around source IP. So in some cases, you'll want to leverage a different persistence option. Some of the other options that you'd use would be something called SSL session ID. Every SSL session, so if we're talking about HTTPS traffic, not Outlook MAPI traffic, includes a unique session ID. Therefore, we can say every request coming from that session ID always persists or is maintained on the same destination CAS server. There's also the concept of cookies. And we've got multiple types of cookies, right? There's a cookie that's generated by the application. You could have a cookie potentially being generated by the load balancer. You might have a hybrid cookie where the load balancer adds additional information to the actual cookie that was generated by the application. So again, if we're talking about browser-based HTTP or HTTPS traffic, we can leverage the concept of cookies. The browser will reply with that cookie and all subsequent requests. Load balancer keeps a table of all those cookies and what the corresponding CAS server in that array is for the destination traffic. There's also some other options around universal persistence and destination address, RDP and SIP, for example. These aren't relevant on the Exchange discussions. Our conversation is going to focus on SSL session ID, the different cookie types, and source IP as your persistence options as it relates to Exchange 2010. The other point we call out is the concept that persistence does not necessarily equal does not guarantee, right, load distribution. Load distribution is the mechanism that the load balancer uses to pick which CAS server you should talk to. And that's completely separate from the concept of persistence, which is ensuring future communications go back to that same CAS server. When we talk about some of these options, there's some technical constraints as well. Cookie-based persistence, for example, is going to require us to actually decrypt the SSL packet stream. That cookie's inside of that SSL session. The load balancer cannot see or inspect those cookies if we have an SSL bridge or a tunnel through the load balancer directly to the CAS server infrastructure. So as we talk about some of these more esoteric cookie-based and SSL session IDs, right, we're also going to have some constraints of whether or not we actually need to terminate the SSL session on the load balancer, and then the question of whether or not we're going to re-encrypt that session as we deliver it inside, or whether we pass that session through as HTTP traffic to our internal CAS server infrastructure. But when looking at cookie-based persistence, one of the technical prereqs is now we need to have a private key out on our load balancer to decrypt the session so that those cookies can be either inspected and or modified for that persistent state table to be maintained. Any questions on the concept of persistence as we're going through? So the next section, right, is we'll actually talk about the concept of load balancing, take all these options around routing and persistence and other options, and apply them specifically to Exchange 2010. And this is one of the diagrams that I find the easiest to explain to people of why this can be a somewhat complex topic. You know, we say you have your CAS server array, put a load balancer in front of it, right? Well, what does in front of it mean? Does that mean clients that are coming from an untrusted network where we might have some security requirements around pre-authentication, two-factor authentication, isolating the traffic in a perimeter network, decrypting it and inspecting it, for example, before we allow it inside? That's a different set of requirements around persistence and routing options, for example, than we may have for internal clients. Maybe internal clients are on a trusted network. We have a separate set of persistence options and encryption options that are going to be maintained or required for internal clients. We also have the discussion, not just untrusted and trusted network clients, but the concept of, are those clients coming from behind a NAT device or network address translation? So do all of our internet connected clients come in through NAT before they talk to the load balancer? If so, we're going to have a significant impact on what our persistence choices are, which we'll show you in a moment. And then finally, in certain organizations that have more than one Exchange 2010 location or servers in more than one location, at some point we may be doing some proxy, CAS to CAS proxy, between those two locations. And when we're doing CAS to CAS proxy, there's some certain scenarios where we want to actually specify a load balancer address or VIP versus just going CAS server to CAS server to provide some redundancy on those cross-site communications. So not just do we have trusted internal clients, untrusted external clients, we may optionally also have the concept of CAS to CAS proxy. The two most common ones, and the ones we'll talk about today, are the internal clients and external clients as dependency on NAT. But from a load balancing perspective, what we're saying here is that you may have more than one VIP. You may have one VIP with a set of security, SSL, encryption options, authentication, for example, associated with your outside clients, and you may have a separate VIP on a separate interface for your internal clients because you've got a different set of persistence options and security options. So when coming up with your infrastructure, it's not just I need a VIP from the load balancing team. We have to look at the concept of traffic flows and possibly break that into a minimum of 2 in this case to provide different security options for those trusted and untrusted clients. We've mentioned a couple times this concept of NAT and how NAT can cause a problem with source IP-based persistence. So source IP-based persistence says request comes in from a client, 7.3 in this case, hits the load balancer. Load balancer then goes through an algorithm. It picks a CAS server in the array. Let's say that it's round robin, the simplest version, right? Round robin says go ahead and pick the first CAS server. Now, all future requests from 7.3 will persist or will stick to CAS server 1. So for the duration of that, of the session, right, from 7.3, the 7.3 will never send a request to CAS server 2 unless we have an outage on CAS server 1, in which case the request will have to be re-authenticated and terminated on CAS server 2. So persistence in this case is working very well, right? Source IP says 7.3 goes to CAS 1. Second client comes up, 8.5, requested to load balancer. Load balancer says, oh, this is a new client. I'm going to go through my round robin request and send that traffic off to CAS server 2. Again, source IP is working great. All subsequent requests from 8.5 will talk to CAS server 2. In our organization, we have external clients coming through a router device before they talk to our load balancer. So we have a router providing NAT from this untrusted network connection for inbound client requests. So an outside client with 8.11 talks to this router. That request comes over to the load balancer. The source IP of that request is no longer 8.11. NAT has changed that source IP to 8.1. Load balancer is 8.1. I have no entry in the table. I'm going to use round robin. I'm going to send the request off to CAS server 3. Another request comes in from outside the network. Talks to our router at 8.1. Router NATs that request, right, to 8.1. 8.1 traffic hits the load balancer. Load balancer looks in the table, says 8.1, do I have any? Oh, yes, there it is in the table. All requests from 8.1 go to CAS server 3. And you can see how this could rapidly become a problem, right, if you've got a large number of clients behind NAT. We have round robin based persistence turned on using, we have round robin as our selection algorithm. We have source IP as our persistence method, but source IP doesn't work very well when there's NAT because all the clients from behind that NAT connection will talk to the same CAS server inside of your array. So if we have NAT and we only have source IP as a persistence type, such as Windows Network Load Balancing, for example, or a load balancer that only supports that persistence method, we will see an overloaded server inside of our CAS server array versus an equitable distribution of traffic across all servers. So clear on the concept of why NAT causes an impact in our persistence types? If we back this up, right, and we said we're not using source IP, we're using cookie-based persistence, for example, The load balancer will look at that second request from 8.5, which is actually coming from 8.1. Look inside the traffic, see it came from 8.5. Okay, I'm going to add a cookie inside of there, give it a new entry in the table, and redirect 8.5 to CAS Server 1. So cookie-based persistence in this case is going to ensure that we have that more equitable distribution because we're not relying on source IP address. So it sounds good, right? You know that we've got source IP, we've got cookie-based persistence, and we've got SSL session ID. So give me a preference. Maybe we say cookie's the best, followed by SSL, followed by SNAT, and I'll use that for my Exchange load balancing configuration on the VIP. There's a catch. When we look at Exchange, we've got lots of workloads, right? We've got Outlook Web App, ECP, we've got ActiveSync, we've got Web Services, POP and IMAP, Outlook Anywhere, Outlook MAPI, Address Book Service, Remote PowerShell, right? All these different mechanisms that people use to connect back to their back-end Exchange server. Unfortunately, all of these different workloads were written by different component teams inside of Microsoft. And we didn't necessarily sit down with all of them and ensure they're aligned. Or in some cases, the IETF standards say that, like POP and IMAP, for example, there's already a set of requirements around how those client types will connect. So we have both a technical challenge as well as an organizational challenge of aligning or simplifying this client access type. So in Exchange 2010, we have this question. Do we use a single VIP for all of these workloads and provide possibly some advanced rules or routing logic to say that the different workload types will have different persistence options? Or do we break it out and we have a different VIP for the different workloads, each VIP specifying a persistence and routing access logic for those client types? Some of it's easy. In some cases, we've got traffic types. We look at OAB, AutoDiscover, POP, and IMAP. We don't require persistence at all. So we don't have to worry about it. If that traffic hits a VIP, it doesn't matter which CAS server in the array the request goes to. That's a one-time transaction. The subsequent transaction can hit a different server in the array, and that traffic type will absolutely work. So we can knock these off the list of having to worry about persistence types or planning for persistence for those not required workloads in Exchange. Then there's some recommended types. Outlook Anywhere, ActiveSync, Address Book Service, and Remote PowerShell. In these cases, if we have persistence turned on, we'll have a reduced performance impact on our CAS servers. With Outlook Anywhere, for example, it's possible, if we don't have persistence turned on, that the RPC data in and the RPC data out channel are established on two separate CAS servers in that array, talking back to the load balancer to the client. CAS has a service, somewhat confusingly called the load balancing service. It doesn't actually do any load balancing. That looks for misaligned RPC data in and RPC data out channels and brings those back together on the same CAS server to fix the problem for you. So if you don't have persistence turned on for Outlook Anywhere, we'll leverage a service inside of CAS. We will keep those sessions aligned, and therefore clients will continue to successfully connect. The only downside is that you generate a little bit extra CPU time on those CAS servers to perform this realignment of RPC data in and RPC data out. Finally, there's persistence where it's required. In these cases, if we do not turn on persistence and have a valid persistence method defined, we will actually see client disconnects, client timeouts, random error messages generated on the clients. So for OWA, ECP, RPC CAS, probably the most common, right, and Exchange Web Services, we're required to have a persistence type defined on our load balancer just to provide the functionality to our clients. So we have a core group of 4 that we have to go through this persistence planning, an optional group of 4 that will reduce the load, and then another 4 that we don't have to worry about in terms of persistence options. So the next few minutes we'll talk about each one of these workloads and what our recommended persistence options are and kind of why that's the case. It gets a little dry for the next 4 slides. We have a great slide after that that summarizes it and shows what our recommended persistence order is by workload, as well as what we've deployed internally at MSIT for persistence orders. So we have a nice summary for you coming up, but I'll walk you through if you have some questions. OWA and ECP, as we said, are stateful protocols. Therefore, we require persistence. The CAS server generates a cookie, so we have the option of using cookie-based persistence here with a application-generated cookie, or we could use a load balancer or hybrid-generated cookie for the OWA and ECP protocols. OWA uses one called User Context. ECP uses MSEXCH ECP Canary. That will show us our cookie type inside. With a load balancer cookie, we just use the insert cookie option. The load balancer will add the cookie for us. As we state though, right, whenever we're doing cookie-based load balancing, we need to do SSL termination on the load balancer itself to provide that option. ActiveSync, as we know, does not require persistence, but if we don't have persistence on, we'll need to re-authenticate as we hit a different CAS server. The simplest way to provide persistence in ActiveSync is the concept of using what we call the authorization header. Every time an ActiveSync request comes in, we will use we have an authorization header, which is unique to that client's request, or that client, not the client request. Therefore, all subsequent requests with that authorization header will be unique to my specific Windows Phone device or iOS device or Android device that's coming inbound. We have other persistence options for ActiveSync, right? You could use client IP. The catch here is I'm not sure the carrier situation in Australia, but in the US, we have a lot of carriers that use NAT. And so all devices coming from AT&T, for example, would have the same public IP address or one or two different public IP addresses. So if we have 20,000 ActiveSync devices, they're all coming in from 2 public IPs. So if the device has a public IP on it, source IP works great because you've got a wide variety of source IP addresses. If your carrier uses NAT and gives your mobile device a private IP address, now we're going to have an issue because all those mobile devices will come from the same public IP, therefore they're going to overload one of the CAS servers in the infrastructure. There's another option, right? SSL session ID. Unfortunately today, we haven't forced people who implement the ActiveSync protocol to comply with all aspects of ActiveSync. So iOS devices today, for example, will spawn a new SSL session ID for different transactions as they're occurring. That would break ActiveSync or cause that performance impact, as now it's going to hit a different CAS server inside of the array. We did announce this summer the ActiveSync license program, which is going to give you a certification list, right, or a groupings of types of devices and the functionality that will be provided. So if you're a level 1 ActiveSync device, right, we guarantee that you'll comply with this set of ActiveSync capabilities. So level 2, a subset of that. A level 3, a superset of that, right? So that's coming. We'll have a little bit more clarity around which features and protocols are supported by the wide variety of ActiveSync partners. Until that happens, though, it's a little bit of testing by device to see which persistence options you may have available. Using authorization header is the simplest one. If your load balancer supports that, that's our recommendation for ActiveSync. Web services is a stateful protocol again. In this case, we can use either SSL session ID, right? Or we could also use a load balancer inserted cookie, or we could use something like source IP if we don't have NAT in the organization. The trick here is what the endpoint or what the EWS app requires. If your EWS app can send the cookie back, we're in great shape. We can go ahead and use cookie-based load balancing. Outlook Anywhere, we had the conversation there. We know that Outlook Anywhere, it's recommended, not required. And unfortunately, we really only have 2 options for Outlook Anywhere for persistence. One is source IP, which will work across all Outlook Anywhere clients. And seeing that this is potentially an issue, we went to the Outlook team. And so in Outlook 2010 now, the MAPI client will submit back the Outlook session cookie. So if you have Outlook 2010 clients, you have the option for cookie-based persistence. If you've got 2007 and prior, your only persistence option for Outlook Anywhere is that source IP. OAB, the recommended one, client IP or SSL session ID, we typically don't see a significant amount of OAB traffic, right? It's only going to be when the offline address books are starting to become substantial in size. Either we've got certificates in the GAL, or we have a very large GAL that we're distributing out to the clients. MAPI and RPC CAS. The only option here is client IP. All of our other cookie-based SSL session ID, those other persistence options, leverage HTTP as the protocol. So if we're coming in with MAPI, we only can use client IP or source IP as that persistence option for our RPC CAS or Outlook MAPI clients. We do recommend the concept of static mapping. What this does is reduce the size of the table in your load balancer's memory configuration. If our source port range is the entire client source port range, we have to keep a table with all of those port ranges defined, which consumes memory and or processor utilization on the load balancer. If we narrow or restrict the port ranges to a smaller set, we then have a smaller state table essentially on the load balancer, and we have a better performance or a cheaper load balancer from our configuration perspective. Steps to do that are going to be different between RTM and SP1. We list you both options right there. SP1, we just allow you to do it in the registry. You don't have to go to the exchange.addressbook.service.exe.config file to make those changes. For RPC CAS, another option that we like to talk about is the concept of Kerberos authentication. We can reduce the authentication traffic on your domain controllers if you enable Kerberos authentication. We released this option in SP1, as well as giving you a PowerShell script to help you manage the service account that you'll need to create to enable Kerberos authentication for your clients talking to an Exchange 2010 CAS server array. As we said, right, we look at the persistence options at Microsoft. We can see here that we have the preferred persistence option listed by each of the workloads, as well as what we've deployed in MSIT. Sometimes our internal group doesn't always align with the PG recommendations due to the fact that we have a challenging Exchange configuration to support. We've got multiple different forests. Sometimes we're doing beta code or testing earlier things, so we don't always align from what a product group recommends to what we do internally, and so therefore wanted to give you both as a persistence choice options. So any questions on this concept of persistence and how to use that for maintaining connections to CAS? The next couple will give you a brief overview of the scaling challenges. We have this concept of what we call a MAPI concentrator. So in the past, client requests went directly to the mailbox server. So if we had 20 mailbox servers, right, they were relatively equitable distributed based on the number of mailbox servers on each mailbox. As we go to Exchange 2010, all client access goes through CAS, which means it talks to a load balancer first. So if we have a device such as Bez, for example, or an archiving solution where all the clients behind that talk to that server then talks to Exchange on their behalf, what happens is, no matter what persistence type we choose, source IP, SSL session ID, etc., all of those requests are going to come from that one MAPI concentrator device, or the 2 or the 3 that we have in the organization. Therefore, all the client requests, which might be in the thousands or tens of thousands behind that concentrator, will talk to the same CAS server inside of that array. And we don't have a solution for this today, right? The option here would be to dedicate a CAS array or a CAS server specifically for that MAPI concentrator, or convince the MAPI concentrator vendor to change to Exchange Web Services or another way of interacting with Exchange to provide a more equitable load distribution across that CAS server array. The other one is this concept of single VIP or multiple VIPs. So we know we might need 2 VIPs at the minimum to talk about external clients and internal clients connecting to our Exchange infrastructure. If we look back the last 20 minutes or 10 minutes as we talked about persistence, we have this concept of do we need now a VIP for Outlook Anywhere, a VIP for Outlook MAPI, a VIP for OWA, for example. This would add some complexity from our user configuration. Now we have different namespaces that the users are using to connect. Those namespaces go to a different VIP, and that's how the users get into that load balancer configuration. So we might have an ActiveSync namespace, a Outlook Anywhere namespace, right, an Outlook MAPI namespace, etc., which adds complexity from the help desk side and user provisioning side around how to ensure that people keep track of using the appropriate namespace. The pro, however, of multiple namespaces is it simplifies your load balancer config. Now, if you want to tune or modify your Outlook Anywhere VIP configuration, you are not impacting ActiveSync traffic and OWA traffic and other traffic types. If you have a single VIP and you need to tune or modify that VIP configuration, and this is, for example, internally, we have a single VIP, and our operations team finds it very complex to make changes because we have a relatively robust rule set around all the different workloads coming into that VIP. So changes to one protocol impact all other protocols. So you have a decision point of, do you want to simplify the operation side, or do you want to simplify the user namespace side of how people connect? Finally, we talk about the concept of SSL offload. And so we kind of briefly gave the description there, right? When do you use it? SSL offload will reduce the performance on CAS for decrypting an SSL session. When do you use it? When your security group wants that traffic encrypted endpoint to endpoint and does not want HTTP traffic coming from the load balancer to the CAS server. One of the things we've seen some customers do to help address the concern of encryption and on the wire versus the overhead of SSL processing on CAS is to use the high bit certificate on the load balancer. So we put a 2048-bit key length out on our load balancer. Clients use that coming from the untrusted network to connect. From the load balancer to CAS, we use a smaller key length. If we use a 512-bit key length, for example, we will see significantly less processing overhead on the CAS server to decrypt that SSL session. So we have the option. Whether you do it or not is typically up to your security group, and whether you want that additional SSL encryption processing running on CAS. It is a little tricky to configure SSL offload. Again, this is done on a per workload basis. So for Outlook Anywhere, we have a commandlet for you. For OWA and ECP, we have a registry key. Once you do that, you can then go ahead and uncheck require SSL over an IIS in IIS. EWS and AutoDiscover, again, have additional steps for turning on SSL offload. Once you complete the steps on these two slides, essentially you're allowing your CAS, or telling your CAS server to allow HTTP connections for these different workload or connection types coming inbound. And finally, one of the last pieces of guidance that we've come up with and worked with is the concept of timeout values. How long do we configure the TCP timeout on our load balancer configuration? The rule of thumb, if you don't have any other guidance, is an hour. Set them to an hour and you should see a reduced number of those random client disconnects or timeouts. In general, to get more specific, with OWA and ECP, it's relatively straightforward. Configure your timeout as long as your longest session timeout. We don't want the load balancer to time out that value prior to the OWA or the CAS server thinking that timeout value has been reached. So if I've got 15 minutes for public and 8 hours for private, those are the timeout values that I'll configure on my VIP for those sessions. EWS, it's based on the app. What does the application expect from a TCP timeout perspective? Outlook Anywhere, go ahead and use the rule of thumb of 1 hour. So, any questions on the load balancer aspects from Exchange around routing, persistence, or SSL offload, or some of these areas? With that, then we'll go in and take a look to see what it actually looks like when we configure a load balancer up against Exchange. So we have a very straightforward, simple demo environment. Let me switch over for you. My demo infrastructure has a Exchange 2010 multi-role servers. We have two multi-role boxes, Fabricam Exchange 1, Fabricam Exchange 2. Those are configured with 2010 SP1, a very straightforward, standard, simple configuration. In general, I don't know if we've talked a lot here at Australia or not, but we're really recommending from Microsoft the concept of multi-role servers. It's very simple and easy to deploy. Your scale unit is another server, right? All server builds in your organization are identical, and you don't have to worry about the ratios of planning, well, how many mailbox to how many CAS to how many hub, and having that breakout. We use multi-role. Our original deployment in our MSIT white paper did not have multi-roles. That was due to the fact that when we did our original deployment, we didn't have the hardware capabilities that we have today. With the number of core counts you get on servers, we'll consume, I think we've tested up to 32 cores. We've seen customers testing in the 40 and 48 core now for a multi-role box. We can leverage or extend that core count as they grow up. But in general, concept of multi-role is simple, easy to deploy. It's easy to add capacity. You put another server in the pool, you add it to your load balancer array, you'll online move or shuffle the mailboxes off to that one. It's seamless, essentially, from a user perspective. And it's easy to add or remove capacity inside of that pool. I have a dedicated domain controller, Fabricam DC01. All these servers are running 2008 R2, and we'll use that to go ahead and connect. We also have a virtual machine running the load balancer configuration. How many of you are aware that you can download a VMware or a Hyper-V VM of most of the major load balancer configurations to do your testing or performance? A few hands going up. All right. So we've got in one of our subsequent slides, we give a link. F5, Kemp, Citrix, all provide a virtual environment, which is essentially, or in many cases, is the exact code base you would get on a hardware load balancer. Some of them are also now supporting your virtual load balancer as a production equivalent. This started a couple years ago as a way for you to test your config in the lab, so you didn't have to buy a 10,000 or 50,000 American dollar load balancing device to have a separate configuration. You ran your virtual machine in the lab, you ran your production one in production. But essentially what we're doing is giving you that chance to run or allow that. So we're running the Kemp Loadmaster series. These are, they retail in the US for about $1,500. You can put two of them into an HA pair and provide that load balancing guidance or load balancing capability for Exchange. We've also done this, if you look at the same session from TechEd North America, you can download the recording. On that one, we did a demo with F5, so you'll be able to see the same concept, a virtual machine, the Hyper-V equivalent of the F5 side. So let's go ahead and launch a connection to our domain controller. First thing we're going to do is validate that we don't have a pre-canned configuration. All I've got here is a Kemp Loadmaster that I downloaded. It's around, I think it's 60 or 80 megabytes in size. You run through setup, it asks you for a license key, you go to their website, give them your name and contact information. All of them want your name and contact info, right? They'll then give you a trial version of it that's good for between 60 and 120 days, depending on the vendor. So in this case, I've went and created a DNS registration record for mail.fabricamtoday.com. So I can see that I have two networks. One of them is my client-facing network, which is the 10 subnet, and I've got a server subnet, which is the 192.168.5 network. So I've got the Kemp configured in a two-arm configuration. So we'll walk through a two-arm configuration with SNAT as our recommended routing option for our load balancer demo today. So let's go ahead and try pinging my mail virtual IP, which is mail.fabricam.com. And I can see that I'm not getting a ping reply on that, right? I haven't configured a virtual IP out of my Kemp Loadmaster yet, so we're not getting any responses there. But what I can do is go to my Kemp configuration here. So let's go to HTTPS 192.168, and on the 5 network, which is my management IP, right, I can connect to that device and get a little GUI that shows me how to walk through it. So I go ahead and connect. It takes 5 to 10 seconds as it initializes. I'll get a certificate error because I haven't installed a trusted certificate on the device to enable that my client doesn't get that cert error. So let's go ahead and click continue to the website. I'm going to enter a credential that I set up on here, which all I did is change the default password at this point. And let's go ahead and see what it takes to configure. First of all, we have two interfaces on this device. Ethernet 0, as we point out, is on the 5 network. Ethernet 1 is over on the 10 network, and this is the one where we're going to configure that VIP. If I look back, I set a DNS registration for 10.46. So if I look at view modify, I can see that I don't have any virtual IPs or what they call a virtual service defined as of yet, so an empty or a blank configuration. So let's go and add a new config. First thing, right, is what I'm going to specify for the virtual IP address. I know that I want that on the 10 network, and I believe my DNS registration was for 46, which is correct. In this case, what we're going to test out is Outlook Web Access, so we're going to test that over 443, not over port 80. We click on Add, and we essentially add that component to the interface. Now, we have some choices, right? Do we activate the service? Yes, we want it active because we're going to attempt to connect to Exchange. Do we need any extra ports allocated here? Nope, it's just 443. In this case, we're going to turn on SNAT, which is done by unchecking the layer 7 transparency. If you hover over the box, it gives you an indication of what that's for. You can also go to the Kemp white paper for Exchange 2010, and they'll walk you through the basic configuration or how we go through this process. There's a health check capability. So in this case, we're going to have it check for the /OA URL. That ensures that the /OA URL is responsive when we do an HTTPS connection back to that CAS server. What that means is that the load balancer is not going to direct a request to a CAS server that's not responding with the, when I do a HTTP GET request to mail.fabricam.com whack OWA. So we'll add that in. We'll give it a service nickname. We'll call this OWA 2010. And go ahead and set, oh, I think I need to set URL here too, sorry. Now let's add in our service nickname, OWA 2010. And we've added in our name. Our persistence option. So we had that long conversation about persistence. Here's where we actually get to go and select what that persistence type is. I'm going to go with source IP because I haven't taken the extra steps to import a trusted certificate on this machine and put the private key on here for Kemp to decrypt it. Had I taken that step where we go through it, we would then be able to select one of the hash options, or which would be a cookie option, right, for a cookie-based persistence for it. I don't have any NAT in my lab, so source IP will be just fine for us to use as a persistence method type. We're going to change the persistence timeout here to 1 hour. And as we come down, we then have the scheduling method. Scheduling method is how we make that next decision, right? So client request that is not yet in my state table comes in. I have to choose which member of the array to send that request to. I have options from round robin, least connection, weighted least connection, or weighted round robin, right? Fixed weighting. Some more advanced options will actually start to look at the individual throughput from the load balancer to the individual machine. So if I see overloaded servers, I can start to offload that or run to others. In general, Microsoft recommends round robin. And you might say, well, that's interesting, right? Wouldn't the most equitable distribution be least connections? You'd be correct. The most equitable would be least connections. That will kind of always ensure you have a steady state. However, what we found with least connections is that when you take a server down from maintenance, you'll run through your drain stop process, you stop new inbound connections to that server, and you take it down, you patch it, you replace a drive or whatever is required. You bring that server back up. With least connections, the load balancer goes, oh, one of these servers has 0, everyone else has 30,000. I will turn the fire hose and send all new requests inbound to this one particular server. And what we found is in a large scale or an org where there's a large volume of new connections, sometimes that server, which has literally just finished booting up, is not ready to accept or process connections at that inbound rate. And so in some cases, least connections will, when coming back from a maintenance period, overload one of the servers for a short period of time and cause some of these random disconnects or problems. Troubleshooting is difficult, right? You just brought the server back up. Within 15 or 30 minutes, people start calling with disconnect problems. You start researching it, but by the time you get to actually looking at it, the problem is gone, right? By that time, the server is up, it's operational, normal connections are running, you check all your logs, everything looks okay, but you seem to have this request coming in once in a while that sometimes people can't connect. So in that case, the simple one is round robin. We will continue to spray evenly or equitably across the distribution. We don't necessarily then have that overload. As we go through the maintenance cycles, we kind of come back to that harmonious state for the number of connections. We'll go with round robin, keep it simple. We know our rule of thumb for timeouts is 3,600 or 1 hour, right? And let's go down. SSL acceleration, we're not going to do SSL offload here, so we leave that box unchecked. And let's go ahead and add some hosts. If I take a look, I can ping fab exch01.fabricam.com. Yep, that's .42. If I look at for server 2, that's 43. Both of those servers should be listening on /OA. Let's validate that. So fab exh1 OA. Hey, we get the OA page. If I go directly to fab exchange 02, I should also get the OA page. I have 2 Exchange cache servers that are listening or running at that. If I go to mail.fabricam.com, right, it should time out because we don't have that VIP running. Yep, we have a unconfigured lab at this point. So let's go to our real server address. We'll put in 192.168.5.42. I think those were the 2 addresses I had, 42 and 43, correct? 443, we want to use NAT, right? We're going to use SNAT in this case for doing that. Add this real server. It's going to think about it. It's thinking about it for a while. Usually adds up pretty quickly. Come on. There we go. Added real server. And let's add the other host, or the other member in our array, 192.168.5.43. Gave me a slight cause for concern there on the, normally it comes up very quickly. So hit OK again. I can see I have 2 servers configured. If I go to view modify services, right, we're doing the health check on the git https mail.fabricam.com whack OA. We can see that the servers are up. Both of them are there. Schedulers round robin. We should be ready to go. So let's try a ping Now with mail.fabricam.com, we see a reply. We now know that the packets are being routed correctly from the client. And the real moment of truth will come when we try to launch a browser to https mail.fabricam.com / oh, and it worked, right? Relatively straightforward. Thank you. That little moment of pause when I was adding the IP address gave me slight cause for concern, but some patience worked out in this case. We should also be able to log in. Let's make sure we can log in. We have a user called, did I call it FabAdmin? I can't remember my administrator username. Yep, Fab. It is funny how your memory brain cells seem to evaporate or eviscerate when you've got a large number of people looking over your shoulder. I'm sure all of you have experienced that when there's an outage or a problem. Let's go ahead and sign in. Right. And there we go. We can log in. We can send mail, right? Our Outlook web app is now successfully load balanced behind a load balancer. The goal really of the demo here is to say that we spent an hour going over some very advanced details. What you're seeing here is a subset of the 2 hours that we cover in the Exchange Masters program around load balancing. And so there's actually, I think, another 10 or 12 hidden slides. If you download the deck, there's some additional information we didn't go over. It is relatively complex, but we've done a lot of work with all the load balancing vendors to ensure that they have templates for Exchange that ensure that you have a relatively straightforward process for actually configuring all of those options that we talk about. In some cases, you may want to take the knowledge we had here and tune or modify your environment, but the simple approach should work relatively straightforward for those demos. For your production environment. So let's switch back. I think we're coming up on time. Here's the list, right? We keep a running list of all the major load balancer vendors. We've also given you a link to their website and or in some cases actually I think it's the next one here. On this wiki site, we have the link to all the Exchange 2010 configuration guides. So we keep a public list of where all the load balancer vendors on the previous page publish their Exchange 2010 config. We've also given you some hyperlinks. If you want to go ahead and download the the CAMP F5 or the Citrix NetScaler VMs, those hyperlinks are active. You can download the trial versions and actually go and run this in your lab environment, which allows you to walk through some of these options without that impact to production. CAMP's had a Hyper-V and VMware one for about a year or two. F5 just released their Hyper-V equivalent of Big IP this summer. So we announced that at TechEd this summer and have that available. And Citrix has one available for you to use as well. So with that, we'll take questions if you guys have any questions. Other than that, thank you very much for coming out. I know we're pushing on time and it's over lunch, so get something to eat, and thanks for your time.